right, everybody, good morning. It is 10 o'clock, and since we have a very exciting and very full agenda, we will go ahead and start now. Welcome to today's webinar on unlocking the scalability of modular thermal energy storage solution, brought to you by the TES Cluster. My name is Emilia Pisani. I am a project manager at RISE, Research Institutes of Sweden, based in Gothenburg, and I will have the honor of being your moderator today with this fantastic panel of speakers. Before we get started, I would like to go over a little bit of housekeeping rules. As you see, you can activate your camera or your microphone during the webinar, but we strongly encourage you to write down your questions in the chat, as you can see there, both during the discussion and the Q&A section. We really want to make this as interactive as possible, so do write your questions. There's no such thing as a bad question. If you know what speaker you want to address, do write their name. And if it's a general question, then we'll bring it up and see who feels brave enough to answer your questions. Please note that the webinar is recorded and will be uploaded to our website together with all the presentations after this, and we'll probably post it on the different websites. As I mentioned before, this webinar is brought to you by the TES Cluster. We are a collaboration of 4 European Horizon Europe funded projects that were funded under the exact same call. So since we have the same goal, the same purpose, and are doing very similar things, instead of competing against each other, we decided to join forces and make it easier for our researchers to share knowledge and find solutions to their challenges together, and as well, and mainly, to collaborate around our communication and dissemination efforts, because together we're stronger and hopefully can reach more people. Hence we have this joint webinar. We also have a joint newsletter, which I strongly recommend you to register for. And we will be organizing a joint workshop in Lipari in Italy as a second workshop we have together. But without further ado, that's about the TES Cluster. Let's talk today about the scalability of modular thermal energy storage. As we strive to decarbonize our energy systems, the goal of reaching net zero economy, our grain of salt in our projects is to maximize the efficiency of buildings by developing compact thermal energy storage. We've seen big thermal energy storage for example, district heating or a network level. The idea is to provide more power, more independence to end users, to building owners, by developing a compact storage, almost like your Tesla wall or your battery, but for thermal energy storage to maximize the renewable energy systems or energy sources you have. A key challenge, one of the main challenges in our projects is to bring these new technologies that have never been done before from a TRL level 3, 4, maybe 5 sometimes, to 6, 7, or even 8. This is great. One thing is to do it in the lab with a prototype, with a pilot where everything's controlled, but to really have an impact in the economy, as we talked about earlier, and to reach a circular economy with using raw material and raw sources based in Europe as much as possible, we need to be able to scale this up. It's not as easy as it sounds. So today we bring here our experts from our 4 projects to talk about our approaches on doing this. We will start, as you can see, with advanced PCM solutions for efficient energy storage. So first, we're going to look at one of the examples of these storage solutions we have, what's in it, and what are the challenges in scaling up. And this is brought to you by Marta Nice, researcher at Technica. Then we're going to talk about the influence of thermal energy storage in building and life and greenhouse gas emissions by Pachi and Hernandez, project manager and senior researcher in Tecnalia, and Aranza Lopez, senior researcher also at Tecnalia. Then we'll follow up on these more technical parts with a short Q&A. Then we'll lift a little bit up and talk more about the viable business cases for these thermal energy storage. And to finalize and open really the question, we'll look at contribution of innovation of thermal energy storage at the European circular economy with Marco Rocchetti, project manager at R2M Solutions. I'll get back to the speakers and the presentations before we get started. So having said that, I would like to open the floor and invite Marta Nice. She holds a PhD in chemical engineering from the University of Basque Country, HPV-EHU. She's a researcher at Techniker Technology Center with experience in advanced materials and their applications in the energy sector. She currently leads the specialization in materials for energy. Her work focuses on the development and optimization of innovative materials to support sustainable energy technologies and industrial applications. As you can see, she's one of the leading researchers in the field. So Marta, thank you for taking the time of being here with us. And can you tell us, in the ECHO project, what are your projects? No, sorry, BEST storage project, my bad. What are the solutions you're looking at within the batteries, the thermal energy storage solutions you're developing?
Okay. Good morning to everyone, and thank you, Emilia, for your introductions. In this presentation, I will show you the development of advanced phase change material slurries for thermal energy storage. First of all, I would like to show you the European energy scenario. This scenario shows that the residential sector has the second highest electricity demand, followed by the industrial sector. Furthermore, electricity consumption in this sector is mainly used to meet the thermal demands as heating and cooling. And in the near future, the energy demand is expected to increase due to the different factors, such as the electrification of the transport sector, also the decarbonisation objectives of the European area, the digitalization, the urban growth, and the economic development. So there seems that we have a clear challenge, that is to ensure the availability of the electricity, preferable from renewable sources, to meet the electricity demand. So this makes it essential to consider the energy storage. As all you know, energy storage enables renewable energy to be stored and used flexibly, ensuring its availability during the peak demand periods. And there is different strategy or solutions to cover the energy storage, both electrical and thermal. However, in the residential sector, where the demand is primarily thermal energy storage is the most suitable option. So it's at this point where the best storage project emerges. One of the objectives of this project is to explore different alternatives to water as a storage material to meet the cooling demand. In this context, the best storage has proposed two different alternatives, two phase change material slurry concepts, which are currently being studied by HYSTORE, Avanzare, and Techniker. The main advantages of these slurries as storage materials are that the storage temperature can be adjusted to match the temperature cooling demand, to have a higher storage energy density, reduce the operating cost, to have a more compact solution, and increase the chiller efficiency. First, it's important to understand the two proposed storage concepts based on the PCM slurry for cold storage. Here you can see the both concepts that we are facing. The first concept is the PCM crystallization concept. In this concept, it's involved to pump a liquid phase change material slurry from the storage vessel through a heat exchangers. In these heat exchangers, the slurry is supercooled but remains in the liquid phase. So, in a specific device known as the crystallizer, the liquid sample is crystallized under controller weights. Inside the storage vessels, to the density difference, the solid and the liquid fractions are separated, and then the liquid slurry is pumped again through the systems. In the PCM concept, the second one, to charge the system, the liquid emulsions is pumped from the storage vessels through the heat exchangers, where the phase change material crystallizes, generating a phase change material slurry. This is a mixture between the solid and liquid PCMs. This slurry is then pumped again to the discharge section where the solid PCMs melts again. If we go in detail for the first concept, the PCM crystallization concept, we have to remark the following features. Only a liquid PCM is recirculated through the systems, cooled or supercooled. In the storage tank, both the crystallization and the slurry is management to take place. And to achieve the true real of the system, we are working with a 500 liters lab scale crystallization vessel using for testing. Okay. And for this concept, regarding to the material, storage material, we have decided to work with inorganic salt, hydrotic salts. These materials are very interesting to the unique properties. You can tailor and customize the phase transition temperature working during a solubility curve with water. So depending on the water or coordination molecules of water, you are able to customize the melting temperature. The main advantages of this material are the high density that they provide, the high latent heat latent linked with the storage capacity of the final system, the safety aspect, and also the stability and the cost of these materials. Up to now, we have selected a slurry based on sodium formate, 39% in weight in water. This material has an energy density of 29 kilowatts hour per meter cubic, what means to have 5 times higher density than the reference material, which is water. Also, we have enough good thermal conductivity, very low viscosity, and we are handling a non-hazardous material in the pH range between 9 and to 11. If we move to the second concept, the PCM emulsion concept, the main features are that the slurry has the phase transition as it passes through the heat exchangers, a slurry containing a liquid PCM during the discharge system, and also a solid PCM charge system is pumped. So we have to manage different properties of the slurry if the system is charged or discharged. And this affects in the operation and also in the design of the full system. To reach the final TRL, we are considered to working with a 600 liters lab scale vessel. Okay. For the PCM emulsion formulation, the formulation strategy is a key part. For this concept, organic PCM has been selected for emulsion formulation in water, and we have to consider the main specification for the slurry. This specification, as we have to have and to manage a liquid with high energy density, we have to avoid or reduce the supercooling behavior of the emulsions, also to formulate unstable emulsions and control the slurry viscosity. All these aspects must be considered during the formulation because they are directly linked with the design of the final system and to select the critical components of the systems, such as the configuration of the heat exchangers and also the pump, which are the key elements of the final system. So during the formulation, the most important properties that we have considered are the stability, the viscosity, and the supercooling. But there is an important question. It is possible to obtain an emulsion that meets all these requirements? Is not? Is there any property that is more important than other ones? During our experimentation, we have found that it was not possible to meet all the requirements defined for the emulsion, the very low viscosity, very high stability, and higher the energy density and reduced supercooling demands. So at the end, we have selected or prioritized three different systems, as you can see in the table, with different main properties. We obtain a very stable slurry with a very low viscosity, but with a not the maximum energy density. Also, we have formulated a very stable emulsion with a high energy density, but with very high viscosity. And the last option was to have a very low viscosity system with a very high energy density, but the stability of this emulsion was not the best one. So we decided to go ahead and to evaluate the performance and the behavior in the laboratory test ring and to evaluate the behavior of these kind of emulsions. And we started to evaluate it with those emulsions with the lowest stability. And here you can see as a summary how the behavior of the emulsion in the test beds. Here we have performed different thermal cycling tests. Here you can see that the stability of the emulsion and the profile of the behavior remains constant, so the stability was quite good. And also we obtain a constant energy stored in the system. With this information, we estimate the energy storage of the system, and we obtain a system with 3 times higher energy density compared with water. And we also evaluate the stability of the system for 90 cycles, and we evaluate the stability of the main material. So, to sum up, to achieve the decarbonization goals, oh, sorry, I have not moved to this slide. So, to sum up, to achieve the decarbonization goals for the European Union, the energy sector requires the energy storage solution. Thermal energy storage is the most way to meet the heating and cooling needs in the residential sector. And in the best storage project, we have developed 2 storage alternative concepts. The first one is a PCM crystallization based on inorganic salts, and the second one is an emulsion based in inorganic PCMs. Compared with water, which is the reference system, we have achieved an storage capacity higher by a factor of 5 and 3 respectively. So to achieve all these results, material science and also the system device design is a key issue to improve the storage performance. And all the new concept requires a redesign and of the operational system to adapt to the new material and to new strategies. So from my side, this is all. Thank you, Emilia.
Excellent. Thank you. Just and even ahead of time. Wonderful. Thank you. Thank you for the really good introduction of the needs at the beginning of your presentation of this, the needs of these thermal energy solutions, because I've noticed we talk a lot about the electrification and deploying, but there is a real balance to be had between electrification and the thermal energy storage. Keep that in mind for the chat. I see there are a couple questions coming in, but I will save those for the Q&A session after the next presentation, as we will hear from Aranza Lopez and Pachi, who will be presenting the, if you take over, right? You will be presenting the ECHO project. Thank you, exactly. So please, Aranza, you are the life cycle greenhouse gas emissions of heat supply in buildings and very significantly across different countries, cities in Europe, from cities with efficient and decarbonized heating networks to those that remain heavily reliant on fossil fuels. The potential impact of thermal energy storage, or TES, on decarbonizing heat supply must be carefully evaluated for each case, and this is what you're working on. In this presentation, you will explore the potential of thermal energy storage, and especially the one for the ECHO, the ones being developed by the ECHO project, to decarbonize heat supply in the city of Bilbao, Spain. Currently, the city's heat supply is approximately 80% reliant on natural gas, presenting a significant opportunity for decarbonization. You will examine how the conventional thermal energy storage and ECHO thermal energy storage, in combination with heat pumps, can support decarbonization. The analysis includes a prospective hourly evaluation of greenhouse gas emissions and the Spanish electricity until 2030. I will not give more details because I don't want to spoil the presentation, but please, Aranza and Patsy, the floor is yours.
Well, good morning, everybody, and thank you, Emilia, for introducing us. Thank you for the opportunity of presenting our developments at the ECHO project. I'm going to start with the presentation and then giving you an overview on regarding the ECHO project and the methodology that we are using. And then I will give the floor to my colleague, Patsy, that will present the preliminary results that we are obtaining. So, thank you very much also to Marta for presenting the challenge that this type of projects are trying to address, which are common among also the storage and ECHO project. But in the end, for the ECHO project, very briefly, we are also trying to develop and demonstrate a thermal energy storage solution. In this case, we aim to cover heating, cooling, and domestic hot water presenting. And in the end, the challenge that Marta presented as well, we are trying to be able to provide electricity load shifting with the aim of covering the peak saving of the thermal and electric load demands. Also, very briefly, some project highlights trying to it tries to address 4 main issues that you can see in the slide. Meaning the energy scenarios and test parameterization, but also the development of storage material selection. Also, we are going to cover the prototype testing, and we are going to demonstrate this in 3 demo sites. And the last issue that we are going to address, which is related with the presentation that we are going to do today, is to simulate this at city level. In this type of projects, we usually analyze the environmental impacts of the system that is under development by itself. But in this case, we aim to scale the analysis in order to try to understand which will be the influence of the thermal energy storage on building life cycle greenhouse gas emissions. For this purpose, we are including in the analysis 3 different cities. So with this, we can understand which will be the role that the thermal energy storage can play on decarbonizing the heat supply at city level. In this specific presentation, we are presenting the results or the preliminary results that we are getting for the case of Bilbao. Bilbao is a city which is located, if you don't know it, in the north of Spain. Well, there are some issues regarding this, but which is most important is that approximately the 80% of the heat supply is covered by the natural gas, which means that it presents a significant opportunity for decarbonization. Regarding the methodology that we are using to in this study, here you can see that we are using the life cycle analysis methodology, which is a very known and standardized method. Here you can see the common life cycle phases that the methodology covers. But here we are using a quite innovative methodology. And this is because we are considering a prospective energy generation at the use phase of the system. This means that we are not only analyzing which is or including in the analysis which is the electricity mix today in Bilbao, or Spanish electricity mix nowadays, but we are also including in the analysis what will be the Spanish electricity mix in 2030, with the aim of including in the assessment this the expected more renewable electricity mix that we will have in the future. And here is when I'm giving the floor to my colleague Patsy, which is going to go further on why it's interesting to include this prospective approach. Thank you, Patsy.
Okay. Thank you, Arantxa. Okay, so can you hear me and see me well? So I will tell you the approach. I will dig into the calculations, like the preliminary calculations that we have done for the eco thermal energy storage, and compare with other solutions that are more conventional, like the one that is nearly covering 80% of the area in Bilbao is natural gas boilers to provide the heating and hot water. So we will compare with that, and we will compare with one solution which is little by little being implemented in some places in Bilbao, which is heat pumps and conventional thermal storage systems. That is a big change, and has many benefits already. So we will compare the three things: the natural gas and the heat pump with conventional thermal storage, and the heat pump and the TES thermal storage, which is the thermochemical storage. So how we will compare? We will evaluate the electricity mix, how it's now and how it will evolve in the future, according to mostly the scenario is aligning with the National Energy and Climate Plan for 2030, but then we extend it a little bit to take into account that these solutions will last for 20 years. So we have this 20 years time horizon, and then we simulate how the electricity mix will evolve. Like in 20 years, we hope to be like more than 90% renewables in the electricity mix in Spain. We are already over 50%, and in 2030 we expect 80%, and in 2045, which is the end of this period of a study, we will be nearly 90% or more than 90%. So as you expect, like the heat pumps will greatly benefit from reduced greenhouse emissions with these scenarios. No? Currently, they are already quite low, and in the future will be even lower. So we will study this scenario. So, like the EcoTES thermal storage, we have prototypes at the moment that the capacity they have like 80 kilowatt hours of capacity of thermal storage. So we will test based on these simulations on a 100 square meter residential building, and then a 500 square meter residential building, and then we compare those two building types supplied with natural gas with conventional thermal storage with different capacities, like for the smaller building 10 kilowatt hours, and for the bigger building 80 kilowatt hours. So that's the idea, is to be able to compare our solution with conventional solutions with heat pump and storage that they use different storage capacity, and with natural gas that normally they don't need any storage, because what they do is like put like a high power boilers, and they don't use any thermal storage. So that's how we will compare. There are a lot of calculations and assumptions. I will try to explain very quickly how we do it. Like to operate in a storage, a conventional storage with a heat pump, you see here in the top the black hourly data, what is the electricity use to operate a heat pump with the storage, and in the bottom one, the yellow one, is like the capacity of a storage going up and down. No? So that's a conventional storage that is charging when the electricity is cheap. And normally, in most of electricity markets, and in Spain, that is the case, when the electricity is cheap, is more percentage of renewable on the electricity mix. So we know that the storage are charging mostly with renewable energy, and this is cheaper and has lower environmental impacts, lower greenhouse gases emissions. So that's the conventional storage with a heat pump charging and discharging in daily cycles normally, and using mostly renewable. And then we comparing if in that building we will use our solution for the EcoTES, the thermochemical energy storage. So this is a much higher capacity that our idea is to develop this. These prototypes are being developed, but the idea is a higher density, so we could use higher capacity in the same building. So you see, in some days we have a larger capacity, so it comes with the capacity and the electricity, the charging. It doesn't work like every day. It doesn't need to work every day. Like it works perhaps some days when the electricity is really cheap and normally they are the same hours that we have like excess renewable energy production. So you use a lot of renewable and then you charge it a lot and then you release it little by little. So that's the idea of a higher capacity of thermal storage, to being able to use renewable electricity for longer time. And if we see the results for that, like the greenhouse gases emissions of these three different options. Of course, the natural gas, we know, like we have, this is in kilograms of CO2 per delivered kilowatt hour of heat. So for each kilowatt hour of heat delivered to the hot water or to the heating systems, a gas boiler, we know it has like 0.23 or something like that, more than 200 grams of CO2 per delivered heat of the gas boiler. And then that will be for the operation of the gas boiler when burning the natural gas. For the manufacturing of the gas boiler is not really much. It's just a bit of metal, let's say. So compared to what is emitted for burning the natural gas is not so much. And then what happened when we use a heat pump and conventional thermal storage? Of course, the blue part, like the emissions and operation, due to the heat pumps using electricity, which is mostly renewable, so they are reduced like fivefold or even more. No, so this is a lot of reduction on the operational emissions. There is an increase on the manufacturing of the equipment because the heat pumps and the refrigerants and the storage systems, they have an impact on the manufacturing. Okay, what happens with the EcoTES system that we test in this building? The operational greenhouse gases emissions, it reduces a little bit. Let's say a bit less reduction than we expected, perhaps. But we notice that we are charging perhaps weekly with these systems, and we use a lot of renewables. But at least the electricity system in Spain, most of the renewable energy cycles are mostly linked with the solar production and are daily. So we find like most of the benefits are used in the daily storage with, for this case study in Bilbao and with the Spanish electricity system. So the EcoTES benefit has a slight benefit on the operation, but just a slight, let's say, and a little bigger manufacturing emissions. Okay, and just to finish up, because I don't have so much time. So if we compare that with a larger area building, applying the EcoTES in a larger area building, we do see that like the operational benefits are not so much because we are more comparable with the conventional thermal storage, but the manufacturing emissions are also similar. So the EcoTES could be, for some size of building, could be an option when you need such a compact system and we need like stable temperatures and some additional benefits that that the thermochemical storage can give you. So these are the conclusions, but I think I already mentioned them, so I will just look at the last one. So there are potential benefits for this compact thermal energy storage. Thermal energy storage in general with heat pumps has a lot of benefits demonstrated, but for the compact ones, there are some additional benefits that we have to make sure that we make focus on reducing the environmental impacts of the manufacturing of those thermochemical storage systems. And some next steps that we still have to test. We are at simulation stage, so we will do some more work for this research with other uses, other cities, and try to estimate the benefits on the electricity network. That's an important issue, that coordinating many thermal storage in the city can support electricity grids as well. So that will be an additional environmental impact for reducing the construction of more electricity grids that we have to quantify as well, but that will be next steps. Thank you. That's all I think.
Thank you very much for these really interesting presentations. And I would like to pick up right away on one of the last things you said, Pachi, of the manufacturing impact. And this is like the whole point of this webinar, is right now it's one thing when you have the manufacturing impact of a prototype of this process is finding the right resource providers, right? How do you see this manufacturing will change when we manage to have a larger scale production with more stable, more accustomed service providers, let's say?
Yeah, I think for thermochemical storage, I think it's still a low TRL, and we still have a lot of research to do. Like even we are at lower TRL than the PCMs, from what I know. And so there is still a lot of improvements to do. We are working at laboratory scale at the moment. So the impacts we were being shown here are at those prototypes. So we hope that we can greatly reduce that if that will be produced as a mass production scale. So the same as we saw with photovoltaics like 10 years ago, that when we did this life cycle impact assessment of photovoltaics, I remember I've been doing that for a long time. And 20 years ago, we see there was like this even fake news that say, "Oh, you never recover the emissions of a photovoltaic in their lifetime." And then we saw that, of course, perhaps in a laboratory setup, perhaps not. But when we go to mass production, we have seen like the huge environmental benefits. So it might be something similar to that. No, we are at the moment the thermochemical storage is. There is not mass production really, but we hope there will be solutions. Like, I am not a chemist, but the chemists in the project, I think they are hopeful that this could be like a technology that could be implemented in some applications, perhaps not for every temperature, perhaps not for every climate. In Bilbao, we see perhaps it's not the best case study to show the benefits, but I think will be some cases where thermochemical storage could be a good solution. And
I think you point out also one of the big things we've seen in the ThumbsUp project, which I'm involved in, is it really depends on the case study. And it really depends on the energy mix and the country. And this is why it's interesting to see and compare. But we actually do have a chemist in the room. So Marta, do you have any reactions? How do you see in the PCMs you are developing this evolution? And do you see that if we manage to scale it up and have larger productions, will that reduce the impact of the life cycle impact of it for the manufacturing process, and in that case make it interesting for more houses to install these solutions?
In the case of working with phase change materials and to prepare an emulsion or water-based solutions, there is no problem with the chemistry to scale up the material productions. Here we have different chemistry companies that are facing the scalability of the production of the emulsions, and there is not a challenge. Always they are finding some problems with the scalability process to produce foams during the emulsion production, but it's not a major problem. This is something that the chemistry could solve. Also, we are considering materials that are safety and abundant. We are not working with critical raw materials or fundamental materials. So we think that this kind of solution could be a realistic option for thermal storage.
Would you say even that it would be beneficial to scale up? That it'll have will it be easier to produce once you produce at larger scale?
Yeah, I think that's easy to work with this kind of materials and the thermochemical materials.
I saw a hand that came up and then went back down. But speaking of materials, there was a question in the chat. If you've seen it, Mark is wondering, did you calculate the cost of these materials being used in the BESS storage solutions?
Yeah. Here we have to differentiate the material we have proposed for the PCM crystallization concept. In this concept, we are working with inorganic salts. This is a raw material itself, working with different water coordination molecules. So this is water and the inorganic salts. The inorganic salts are cheap, and the cost of the final material, just the slurry, it's around 1.3 euros per kilo. This is working with the commercial material. And in the case of the organic PCMs, it's true that the paraffins has a higher cost compared with inorganic salts. The cost could be around 10 to 15 euros per kilo. But here we are preparing an emulsion, and the maximum PCM content in the emulsion is around the 30% in weight. And the cost of the final formulation, considering the surfactants that we need to increase to promote the stability of the solution, the nucleating agents to avoid the supercooling, the final cost of the solution that we are managed is close to 4 euros per kilo. So the cost is higher, but we are handling different kinds of material and different kinds of concepts.
Interesting. Great. And how do you see, to both of you, this, Betsy, you went into this a little bit more in detail, the use of these compact thermal energy storage together with other existing technologies, sort of as leveraging and finding synergies. Is this something you also see in the BESS storage? And how do you think we could maximize this what we call I would call sector integration, whereas like you have an energy source and how can you store it in different ways depending on the needs, depending on the location, and with the different using technology. So you look at the system as a whole and not just the individual solution. How do you see this? How do you see this being beneficial, or is it an accelerator, could you say, or is it just, do you see a linear progression?
Sorry, was that for me, Emilia?
Oh, that's to either of the three of you. If you dare.
Yeah, I see. Like, of course, the thermal energy storage solutions have been there for a very long time, and conventional thermal energy storage, like the water storage, we see them in most buildings, perhaps not in the ones with natural gas boilers that are more instantly operation. But yeah, the water thermal energy storage is This already has a lot of benefits in combination with the heat pumps, and taking into account how the electricity mix is very variable, increasingly variable, because we have more renewables. And if we use that through heat pumps and storage that heat, that's recognized multiple benefits, reducing the greenhouse gases, benefits to the flexibility of the electricity grid. So we have plenty of benefits there. And then these new technologies come in, and so we compete with this conventional thermal energy storage solution, which is storage in water. So that's our main competitor, let's say, which is fine. It's a good competitor. Water is really cheap. It's not corrosive. It's very easy to use, let's say, as a thermal energy storage. What's the potential benefits we could give? The integration with the system will be similar, with slightly additional benefits, like, for example, the space is one of the aims. Like, we have this innovative solutions. If you see here in the presentation, it's compact and modular thermal energy storage system. So we want to do it in using less space than water. We want to use it in perhaps in ranges of temperature which is more stable, like, because both thermochemical and phase change materials. So the reaction is a stable temperature that we can control. Like the water storage is fluctuating. To give the heat, you have to fluctuate more the temperature of the water tank, and the velocity of the discharge could be another potential benefit of these systems. So you can discharge them quicker. So those are some potential benefits of these innovative solutions. But regarding the integration with a bigger system, like the benefits are similar. So about the integration more renewables, so flexibility to the grid, it will be similar to bigger water storage tanks. But in here we do kind of additional benefits, and hopefully the benefits of the space and more stable temperatures, and perhaps a slightly increase in the efficiency as well, because of those stable temperatures. Those are additional things we try to put into the system. Yeah.
Thank you. Yes, about the charging and discharging, I'm saving that question for after the next presentation, and I will use that to introduce our next speaker, representing the ThumbsUp project. Stefano Barris, Dr. Stefano Barris, received his PhD in turbomechanery and advanced energy system engineering at the University of Genoa, where you're working now, in 2016. Stefan, are you here with us before I start introducing you?
Sure. Thank you very much, Emilia, and good morning, everybody.
Good morning.
The goal of my presentation is mostly to, take a look at the possibility to apply, let's say, our thermal energy storage that we are developing in ThumbsUp project into, let's say, different type of buildings and different type of markets in order to develop viable business cases. So in my presentation, just a few words maybe about ThumbsUp. The idea is that in this project, we are going to develop two types of thermal energy storage. One that we call fractless, that is based on latent heat, so PCM, and actually bio-based PCM. For example, lauric acid, or let's say acid and paraffins that can come from let's say nature, like natural waxes or fatty acids from leaf stalks application, etc. And the second one is a sorption-based thermal energy storage that we call TES, that has the goal mostly to work more on, let's say, a longer duration thermal energy storage application based on a sort of thermochemical application. The idea is that our thermal energy storage can work not only to maximize, let's say, the the efficiency of the heating system, but they can also offer the possibility to work on power to heat applications, and let's say facilitate the maximization of self-consumption of PV rooftop, for example, in a building, in order to use this electric surplus mostly to cover heating and cooling demand. We have a quite relevant replication, let's say, replication approach that we would like to apply in the project. I think that there has been a mistake because I prepared a different presentation. Maybe I attached another one. So may I share my screen? Sorry, because I cannot find the correct one. Sorry, most probably it's my fault, but I cannot recognize my slide, Emilia. Sorry for this. This is the nice stuff of the how can I say, the
introduction.
Sorry for this.
No,
sorry for this.
Things happen.
Sorry
well,
for
you continue showing your screen. I can finish introducing you.
Yes, I
or
can.
You have the now.
Yeah,
you
yeah.
have it.
Yeah, I have everything there. Sorry. So as I was stating, the idea is that we are going to develop these two types of thermal energy storage solutions. One based on phase change material, as you could see in the slide, also quite compact as a sort of box that you can put in your domestic warehouse, for example. And the other one named Sortes, that is, as I said, more for long duration, that is based on a sorption test. Both the solution, as I mentioned, are very sustainable from an environmental point of view because they are based on natural materials. In one case, as I mentioned, fatty acid. In the other case, water-based and zeolite solutions. The goal of the project is mostly to work strongly on validation and demonstration. We will first validate our solutions in Cardiff Research Center at a more, let's say, compact size, but we will then go into the real demonstration cases in single-family houses in Spain, in multi-family houses in Spain, and also in multi-family houses also connected with district heating network in Sweden. As you can understand, we are already in our demonstration campaign targeting different type of buildings and different type also of connection with heating and cooling solution. Why this? Because we strongly, as I mentioned earlier, focus on the replicability of this technology. So we don't want to make a demonstration that is, let's say, just for the project. We really would like to check and see which are the best type of buildings where to integrate our thermal energy storage solution, which are the best, let's say, energy markets. Also, I would like to say energy market boundary condition where our thermal energy storage can be effective, and also if our type of thermal energy storage can coexist, for example, with other type of energy efficient for heating and cooling solution, like, for example, district heating network, and most of all, heat pumps. As I said, the project is very focused in replication, and we are targeting a replication campaign where we will study via simulation tools the application of our technologies that we tested, as I said, in Spain and Sweden, also in the Netherlands, in two different type of buildings in Italy, both single-family houses and multi-family houses, and also in Greece and Estonia. So also checking different type of climates and energy context. If we would like to implement our ambitious replication cases, ambitious replication roadmap, of course, we need viable business cases. As I mentioned before, we need to investigate which are the best energy market conditions, but also which are the best, how can I say, building sizes and conditions in terms of heating and cooling installed application. Also because theoretically, our thermal energy storage can be applied both in retrofitting, so in already existing buildings, as well as in newly built buildings. In this sense, as University of Geneva, we worked on thermoeconomic model in order to investigate our business case, in order to understand, therefore, starting from the analysis of the demo site, if our thermal energy storage can be effectively supporting and of the decarbonization of the heating and cooling system in the buildings, but most of all, if the thermal energy storage can develop viable business case. Here you can see a sketch on our VUECOMP modeling suite, these thermoeconomic models. And also what I would like to state is that our technologies are, as I said, effective from for example, energy storage capacity point of view, compactness of our storage, sustainability from the environmental point of view, but at the same time, they do have some cons, they do have some drawback. One is, for example, that while the energy storage capacity is quite high, even with limited volume, if I would like to keep a limited volume, unfortunately, the thermal power capacity is limited. So I cannot exchange large amount of heat with between the heat pump and the thermal energy storage, or between the demand, the heating demand, and the thermal energy storage. Furthermore, for what it concerns the SORTES, so the sorption-based solution, we should need to consider to operate the system to have it effectively, to exploit it effectively, at least to charging for minimum 3 hours along the days. So these are the technological limits. There are also technological limits related to the maximum state of charge and the minimum state of charge. And knowing these constraints, we implemented and we sized, thanks to VUECOMP, we tried to size, starting from the real thermal energy demand of the different buildings, of the different demo site of our project, we sized the optimal size of both the fractless and the sortless, having in mind that theoretically the fractless should operate more at daily level and the sortless more at longer duration level, like weekly based, etc. We operated, as I said, on a week based, so we took a typical week of the heating demand of all the heating months of each building, that we do have this type of information from our demo site, and we sized the different tests for all the buildings. For example, in the case of Cardiff, we saw that the role of storage has been mostly to maximize the PV self-consumption and to store the excess of PV production, particularly during the weekends. Another role that the tests did have was to optimize during the peak moment of the demand the heat pump operation towards higher COP. So we were moving towards nominal COP. So in principle, the idea was mostly to work, in this case of Cardiff 3, both on, due to the fact that in the weekend the building is not working, maximize the operation along the weekend and exploit the PV production that otherwise would have been wasted, as well as to optimize the energy efficiency. As you could see, from a CapEx point of view, our solutions are quite important, and therefore, unfortunately, simplified payback period are not so effective. You can see that they are higher than 20 years. So in all our simulation, we considered, also having in mind that one of the goals of our tests is to work in power-to-heat application to maximize the PV self-consumption, we considered some incentivization schemes like the Italian one, the Renewable Energy Community Italian ones, that remunerate each megawatt hour of PV that is self-consumed with €100. If we consider this type of incentives, as you could see, the payback period drastically reduced. We did similar analysis with multifamily building by Veolia in Valladolid, where, differently than Cardiff, has no major weekend effect due to the fact that obviously the buildings are used all along the week. And here again, in any case, the role of the storage was to maximize the PV self-consumption and optimize the COP in the peak moment. Again, as you can see, unfortunately, due to the high thermal demand of the building, because it's a large-scale building, we do need large investment for what concerns CapEx, and the savings are not so large. So the payback period, even with the incentive, are not so promising. If we look at the single family building of our demonstration project, we are dealing with a very high efficient building, with a very low heating demand. And in this case, for example, at the end of the day, the role of the TES is mostly has let's say, tool that enable a maximization of the PV self-consumption. And in this way, as you could see, indeed, without the incentives on the self-consumption, the payback period is very, very, very bad. Last but not least, an important case is the Swedish one, where we are somehow competing with district heating network. Actually, what is interesting to say is that there is no conflict with district heating network because of the fact that the cost of district heating network thermal energy is higher than the cost of electricity. And here, as we are working with a heat pump that, as you know, is a sort of multiplier of energy, I mean, from electricity to thermal energy, at the end of the day, the TES can work effectively, not competing, as I mentioned, with the district heating network. So here, for example, in the case of HSB in Gothenburg, the role of the TES was to optimize the peak moment of the heat pump towards higher COP, and also in mid-season, maximizing the photovoltaic cell consumption, even if you have to consider that in the case of HSB, we do have also a battery. So the role of, the TES was mostly to cooperate with the battery, particularly in periods where heating and cooling is prominent. So if we, just to wrap up, as you could see, we can state that if we can somehow use our TES as a sort of daily or even weekly shifting solution for PV maximization, this could be the most relevant purpose of our tests, particularly if we are able to exploit incentives. And, if we can also, if we have high efficiency building with very low heating demand, this can be really the only way to exploit the tests from a remunerativity point of view. What I would like to say is that we, according to this analysis, we can try to extrapolate some guidelines for viable business cases for application. One is the fact that due to high capex and limited thermal power heat capacity of our thermal energy storage solution, we should really wisely target which are the demo site, where, let's say, not the demo site, the buildings where we would like to integrate our test solution, as our tests are quite capex intensive. And according to the presented thermoeconomic assessment, it is clear the importance of perfectly sizing the thermal energy storage with the size of the heat pump and with the size of the photovoltaic in order to minimize the payback period. In this sense, it's easier for sure to set up viable business cases more in newly built buildings where we can play on each the pieces of the puzzle more than in retrofitting, as we are doing in this sense. What is also crystal clear is that power to heat for this type of storages that are capex intensive is the key function from a remunerativity point of view, more than maximization of increasing of the, let's say, energy efficiency of the heating and cooling system. So most probably, ESCO business model, for example, for this type of technology are more complex to be applied, while other type of business models like aggregation or, let's say, more electric market-oriented business schemes could be more viable, also having the chance to maximize self-consumption incentives like Italian Renewable Energy Community or other type of self-consumption incentives that are currently promoted in Europe. I hope I have been, let's say, concise and clear.
Right on.
Thank you for your time, and if you have questions, I'm here.
Thank you
and
very
sorry
much,
again
Stefano.
for this technical problem.
I think it's there's no webinar or digital event without, or physical event without some sort of
we brilliantly covered it in any case.
So thank you very much. There will be questions and I hope a discussion, but to allow Marco to have enough time for his presentation, I would like to hand the floor over to Marco Rocchetti, who is a certified energy manager and mechanical engineer with extensive experience in energy efficiency and renewable energy integration. He graduated from the RIDEF course at Politecnico di Milano and the IUAV in Venice in 2007. Rocchetti has worked in technical scientific tutor and master's degrees, held courses on energy policy and management for FESR projects. And since 2014, he has been working at R2M Solutions as a partner and project manager for the European projects and currently serves as head of energy and technology area. So Marco, thank you very much for taking your time and being here with us. And what I look forward to your presentation, we have scaled from the smallest, we looked at the PCMs in the battery, how these batteries work in Bilbao together with heat pumps. Then we looked at the different use cases and pilots from ThumbsUp. And now you're going to lift our heads up a little bit and look at the European level and how these solutions, what we need to take into considerations, what are the lessons learned from other technologies to be able to really get to a net zero economy and have proper circular economies. So Marco, the floor is yours.
Okay, thank you, Emilia, and good morning to everyone. So as anticipated by Emilia, I want to move the attention from the use cases to the business modeling that can support the integration of thermal energy storage at European level. In doing that, I want to present the HYSTORE mission, that is a European project funded on the same call of the sister project and started in January 2023. Here you can see an image with some partners, some countries and partners participating in the project. The scope of HYSTORE is to validate and demonstrate at economic and technical level the integration of TCM solution, thermochemical solution, and PCM solution inside thermal storage, and integrate this solution to the grid, exploiting grid services. This is the innovation that we want to demonstrate in the project, and in order to facilitate the integration, we want to demonstrate that the added value of this kind of solution are not only at building level, but can be extended at the local group of buildings or network community level. Some objectives here want to demonstrate to have a plug-and-play solution for different climatic zone. We want to validate the solution at pilot level in Sweden, Spain, Austria, and Ireland by an optimized strategies for the control of the building consumptions. The objective number 4 will be the demonstration of scalability and replicability of this solution and the integration at building level. Some impact. We want to achieve 120% energy density respect to the water-based solution. We want to reduce the capex more or less at 50% respect to the common thermal energy storage, obviously not considering the water-based solution. We want to enhance installation efforts, and our approach will be to provide a solution that can be competitive with lithium batteries. So this is probably a big challenge. In the context, or in the European context, how we can imagine this kind of solution. So we have to think about the European context and the priority that we need respect to the energy sector and the not only residential sector, but at general level. So we can see that at the moment, looking at the European level, we have a strong dependency, energetic dependency from non-European countries. And this problem is not only related to the energy. So we have the same problem from raw material and technologies. For example, some strategic materials, lithium, cobalt, etc., and some technology that we have not able to produce inside European countries. For example, lithium batteries or other kind of electronics components that are fundamental for this kind of sustainability. We have a lot of geopolitical risks that create market instability and cannot support security for the entire value chain. And as all of us have seen in the last month, we have a lot of discussion about customer duties that can create other conflicts at economic level with non-European countries. So these points are fundamental for define a strategic approach, and we have to think about a different kind of business model in order to create a strong energy and technology value chain inside Europe. The approach that I want to push is the circular economy that can mitigate risks, reduce costs, in particular way if we have to pay duties and taxes, and enhancing internal results. So we have to increase European knowledge about this kind of technologies. An example of the problem that I have already presented are shown in these slides. On the left, you can see a map with European policy conflicts, instability, and on the right, a map with countries that hold the raw materials. If you note the countries with the conflicts and the geopolitical instability are the same that hold the raw materials. In this case, I presented the raw material for the production of lithium batteries. It means that if we want to implement a sustainable business model, we have to choose another way. So we cannot base our economy on countries, on the relationship with countries with instability, because it means that we will not produce a sustainable model. An example of the problem that can be generated by this strong dependency is this one. For example, I have presented the Nord Stream attack and the effect that this instability, policy instability, can generate in the market. In this case, in the European gas prices. Here we have seen that the cost of the natural gas passed from 25 euro for megawatt hour to more or less 250. So it means that these changes create instability not only at residential level, but in the whole European economy. It means that we have instability in the production of goods and services, and obviously this is reflected everywhere. So if we want to reach the goals, the sustainable goals that the European Union promotes, we have to push circular business models that are an innovative approach for produce goods and services in a sustainable way without a strong dependency from outside the countries. It means that we have closed the loop with resources that are available inside Europe, or we can generate inside Europe by different kind of strategies. Some pillar strategy are recovery of goods, regeneration of technologies, goods, and recycling. So the recycling is fundamental in order to promote the sustainability of not only thermal energy storage, but energetic technologies. Another point is to develop a sustainable design, because we have to think about circularity from the beginning of the business model. We have to promote maintenance in order to guarantee the circularity. Second life is an important strategy, and reverse logistics that are fundamental to maintain the circularity. Added value that can be created by this approach are not only at environmental level, but are reflected at economic and social level. Now I want to present the applicability of this circularity business model at thermal energy storages. Storages in general are already included in this kind of business model. For example, we have seen that these approach are already available for lithium batteries. That is a consolidated example of sustainability. And the approach is to collect positive feedback, positive experiences from this kind of consolidated technology, and push this business model to the thermal storages. It can promote the recovery of it from industrial processes, and the integration, obviously, from district heating and network that can create a positive as I can say, booster for the circularity of business model and the integration of thermal energy storage in the European market. In terms of policy that can facilitate this approach, I want to present here the standard producer responsibility that, from my point of view, is fundamental to push this circularity business model. The standard producer responsibility is an environmental approach that connects the recovery of the goods to the producer. This is at the moment a voluntary approach in some sector, but in other sector it is mandatory. It is important because it can facilitate the circularity. On the right of this slide, you can see the different phases that we have to take in consideration if we want to improve this approach. For example, by the use of raw material, we have to start thinking about a circularity design. It means that we have to design a product that can be disassembled with easily disassembled, so it's probably the best thinking. The production have to follow this approach, the use into the market, and then the recovery. The recovery in this case is responsibility of the company that produced the goods. And then we can follow two different ways. We can recycle some raw materials, obviously not the entire product, but we can disassemble and recycle material that can be reused in the second life of the material cycle. For now, we can see that this legislation is included in other European core legislation. For example, Waste Framework Directive, the Packaging and Packaging Waste Directive, Directive on Waste Electrical and Electronic Equipment, and the Battery Directive that is one of the most important integration where we want to focus the attention. Okay, future, as said, this is becoming mandatory for all state members of European context. The target are based on collection, recycling, recovery of raw materials. And it is another good point to mention that this approach can facilitate the reporting, the transparency that is an obligation from producers. So it means that this is not something, so this is a positive approach that can facilitate also other industrial activities. yes, here you can see the impact that this extended producer responsibility can have at European level. It can facilitate the rate of recycling inside Europe. It can improve the producer accountability and generate sustainability also in other sectors, because it's important to extend the circular economy also with other industrial sector. It means that with the extension of this approach, we can increase a lot of the benefit that one circular economy can generate. It's important that at European level, we will reach an harmonized level across the member states. And another point that can facilitate this approach is the product passport that in some situation it is mandatory, for example, for batteries, lithium batteries. Analyzing the literature, we have seen that this article is very important. This the title is Enabling the Circular Economy of Solar PV throughout the 10 hearts of sustainability. I want to focus the attention now on the why we are analyzing PV articles and lithium battery articles or literature review. The answer is very easy, because if we want to put in place a good strategy, a good business model, we have to compare our idea to consolidated business model. So thermal energy storages at the moment are innovative for the market. So also if they are based on consolidated technology, the integration of these goods inside the market at building level, at industrial level, is not is a niche market, is not a consolidated market. So we are comparing this model with the PV and the lithium batteries business model, because we can consider them as a consolidated models. In this article, we have seen that we have 10 Rs that represent 10 pillars for the implementation of circular business model in the PV production, and 3 important parts start from the beginnings, from the technology design that push the rethinking approach. So we have to think that something that can be reused after the end of life. The raw material collection, that is the second part, push the reducing from new raw materials, so from reducing from the in a lot of situation from outside Europe countries. And the third pillar is the definition of technical specification that have to push the reuse approach. So it is good strategies for implement circular business model. Now I want to present 2 use cases.
And this we see very much in the technologies being developed. I know you have a couple of slides left, but I'm going to kindly ask you to go quickly through them so we have time for a little bit of discussion in the end. Thank you.
So two examples. So the first is First Solar, that is a leader for thin PV films. They implemented this approach and use raw materials for the production of other goods, for example, glasses, semiconductors, or encapsulament materials. And on the left, you can see the efficiency that they reached, reducing 90% of material recovery. Another good example related to the batteries is the MIDAC approach. Here you can see the application of a second life approach. It means that by the standard responsibility, they can decide to reuse batteries, obviously not with the entire capacity, but from the automotive sector to the stationary sector. So this is two interesting approach that can facilitate our business model that is presented here. We think about producer that can be a newco that want to operate into the market with the standard product responsibility, and it means that we are we have to sell the product. We can create a relationship with the customers, and we are responsible to withdraw the goods at the end of life. At this point, we have to choose if apply second life approach or the disassembling. Disassembling means that we need to have a strong relationship with a recycling company, and from now we can see that the cycle can be closed to recycling of raw material and the reuse of the same in other industrial sector or in the same industrial sector. I want to conclude with some strength SWOT analysis. We have seen that thermal energy storage is an opportunity to increase the energy density for storages. We can enable energy flexibility by sector coupling. We can use a human-centric approach and create environmental benefit. And obviously, this is an opportunity to create leadership and independence from the European countries. Weaknesses are obviously represented by the market, that the market flexibility is not harmonized inside Europe. We have not a lot of experience in operation and maintenance cost, and obviously, as seen in previous presentation, CapEx costs at the moment are very high respect to the common technologies. So that's all for my side.
Thank you, and it's always a pity to have to rush through the last presentation. So thank you very much. I'd like to invite the other speakers to turn on your cameras now, and we stop sharing. There you go. Thank you, Marta and Arantxa and Patxi. If you want to turn on your cameras, we have 3 minutes left for the discussion. And so I want to ask you how you see the main role of thermal energy storage in the future of the building market. And we are looking, and the importance of looking at the buildings, at the end users, being able to empower them in putting in place this energy transition we're all striving for. Marco.
Yes. From my point of view, the role of thermal energy storage inside the building are fundamental because we are moving from a digitalization of building sector. And in this way, thermal energy storages are sector coupling technologies that can facilitate the energy flexibility, the integration of renewable system, and an opportunity is to reduce the costs that we have seen that are very high, but we can generate additional value, for example, from the flexibility market that can reduce the payback time. So it means that probably as seen from the PV history, TES technology can follow a similar approach, so can become a fundamental technology in each buildings.
Thank you. And Stefano, how do you see will we be able to get over this high CapEx? I think Stefano and Patxi, this high CapEx or manufacturing costs of these technologies, do you see a way to reduce them, or is it going to remain a challenge in the next 5 to 10 years?
In the case of our ThumbsUp solution, for sure, one, let's say, bottleneck is the material itself cost, that the cost of the material is higher in this moment, mostly because there is not yet a large scale market. But if we think of the fact that we are dealing with bio-based solutions where, as I said, for example, fatty acid are a sort of byproduct from the food industry, this type of material could cost much less. And furthermore, other types, for example, again, in ThumbsUp, we are developing this heat exchange that try to optimize and maximize the heat exchange with the PCM as well as with the shortest matrices, this type of heat exchangers could be manufactured more in a cheaper way, particularly via advanced manufacturing technologies with chemical etching, for example, for the sizing and design of the plates of the heat exchanger. So for sure, there could be the possibility to reduce the cost of this type of storage. But obviously, let's say, the traditional hot water tank will be always, let's say, cheaper than them, but obviously with less performance.
Marta, how do you see the evolution? They've mentioned, okay, the need for a market for these raw materials. Do you see an evolution in your field of that there are more and more of these fatty acids and salts available in Europe, produced in Europe? Or how do you see the market there? You're muted.
Sorry. In Europe, there are several companies working with phase-change materials, and also they are changing the strategy of their mine because they are also trying to find bio-based phase-change materials. Bio-based because the raw material is fatty acid itself, or maybe trying to recover waste products and obtain from these products a new valuable materials that could be useful as phase change materials. So I think that this kind of material could be an option. Europe has the industry, has the knowledge, and also has the legislation that could promote the use of these kind of materials.
Excellent, thank you. Unfortunately, we've run out of time, and we would like to get your opinion on this event. So, Beñat or Sophia, would you mind sharing the last slide with the QR code? In the meanwhile, I would like to thank everybody for your time. First of all, the speakers, thank you for taking the time to prepare, to share your knowledge with us, to get some ideas planted in our heads. I hope you all enjoyed this hour and a half that passed really quickly. Thank you to the different projects for collaborating, and it's been a really enriching experience on my half. And to all the listeners and participants, thank you for listening to us, for being here. I kindly ask you to take up your phones for once and just scan the QR code. Let us know what you think about the webinar because it will help us prepare. We try to do this twice a year, once every semester. And so please do look out for the next ones. And for those of you who are interested in the more technical phase change material, technochemical material, a follow-up on this webinar is going to be a in-person workshop in Lipari in the frame of the ISEC conference. I will put the or Sophia, would you mind putting the link in the chat for the Lipari conference? And if you're going to be in Lipari in the conference, do join us, and it will be a whole afternoon with all our technical experts to try to address these challenges we're facing together. I would love to get your feedback. So thank you very much. Thank you, Sophia and Beñat, for organizing, for putting all the back work. You never see it, but you've done an amazing job. Thank you, Stefano, for your time. Marta, Marco, Aranza, and Pachi for your presentations. Having said that, we're 2 minutes over. I wish you all a lovely rest of the week, and do continue following us for more exciting solutions. We'll see. We have a year and a half left to see if we manage to overcome these raw material and CapEx challenges. Thank you. Oh yes, one last thing. The webinar is recorded and will be available along with the presentations on our websites and social media. Do follow us.